In the previous videos we have shown that all masses has some sort of medium surrounding it. The Earth, for instance, has a strong medium surrounding it, which is following the Earth through the space. We have also shown that this medium must be made up of some sort of objects, which we call daon. It's a unique object, very many of them, which are filling up space and gives a reference frame to everything. So the special relativity, we have shown that that was wrong in the sense of its reference space is wrong. You can still use all the equation of relativity theory if you like, but only on the surface of a strong or big mass which has a strong medium. In this case it works perfectly well. Okay, we have also seen that these daons, if you arrange them correctly, can make up an electron, as you can see in this image. Why do we choose an electron? Well, in fact, according to Maxwell's equation, the charge is the base for all electromagnetics, and also the electron is a sphere, must be a perfect sphere, which means that it's quite easy to treat from mathematical point of view, and so we will keep on using the electron as the mean to bring forward this electromagnetics, because the electron also contains all unknown in physics today. That is what is a charge, field, potential, etc., magnetic field, etc. So we will continue with the electron, and then later on we can extrapolate the result to all particles or all charges. Okay, so you have this image that you see, the electron, how is it made up? Now, first you should also know that since the electron is a perfect sphere, and also that we don't see any granularity in the reaction between different charges, that means that the daons which are making up the electron must be very small compared to the electron. You have also, if you look to the equations of field and potential, that these formulas are valid only at a certain distance away from the charge. And also you should see that these equations show that you have a constant force between the different layers or shells around the electron. If you come up to a certain distance, then this value of force between the charge must become constant. And this is what you see also in this equation, for instance, of field or force, which is divided by r squared, which means it's the surface of the sphere. So it's a density more or less, which means that the force within the shell is constant. Okay, so we can now show calculate the number of daons in the shell. We get this equation here. So this is just the surface of the sphere divided by the surface of the daon, corrected with the filling factor. The filling factor is just because the surface is not completely filled within the shell of daons. You have some open space, let's say, which is you have to correct for this, and this is a filling factor for a plane surface with spheres. As you see in this image, you have also that the daons must be placed in a specific geometry between layers. This is a typical sphere, equal sphere geometry, and this you can use because since the daons are very small compared to the electron, you can forget about the curvature of the surface, because if you look just between two daons, they are the curvature is so small that you can neglect it at a certain distance. Okay. Now, if you continue to reasoning about the daons, you find that since it's a sphere is proportional to r squared, the further you go away from the charge, the weaker is the interaction between daons to keep the force constant between shells, which means that you go very far out, then the order, let's say, of the daons are very weak, so they are moving around, they are maybe replaced. The shells stays in place, but you have that the daons can be exchanged, can move around, etc. But for the equilibrium of the force around the charge, you must have the shells in the same position, even if the daons can move around a bit. You will have, when you move very far from a charge like this, you have also interaction with positive charge, so that you have a zero field at a certain distance, but the space is always filled with free daons. We call them free because they are not have no specific order, which means that the space as such is filled with free daons, we call them. This is quite important, and we will use these specific daons. They come back in the equations very often, so we will use this name free daons for them, and later on we will be more specific about these free daons. Okay, so if you now look to the picture of this electron, you see that to have an equilibrium of force on the shells, you have to have that each daon must be an equilibrium. That is, within its own shell, of course, the daon is in equilibrium because they have equal strong force all around. And from the layer up or down, you also have to have the same force pushing radial outwards or inwards. So you get an equation where you have that the force should be constant, and you obtain that you have 3 interaction points between the upper and lower layers and 1 daon. And you have 6 daons surrounding it in its own shell. So you get this type of equation here. This is, you have that you have n is the number of daons, AD is action of a daon, let's say. Cosinus phi is the radius, no, the angle between the radius of the electron and the interaction zone of the daons. This is square root of 2/3. And you have then the sinus xi, which you can see in this figure here as defined. This comes from the curvature. It doesn't, it's extremely weak when you're far away from, you can neglect it when you're far away from the charge. But if you close into the center, then this xi starts to grow. And it has an important role up to play because you have the forces going down. The charge is reduced, let's say, when you come into the center of the electrons. This is quite important, but just close to the center of the electron. If you are far away, you can forget about it or neglect it. Okay, so when you are far away, you can then express this quite simple, as you see here in this equation. Cosinus psi is average coupling. That is, we saw already when you have the angle between the rotational axis of the daons, and this we call psi. And so when you have a shell of daons, the interaction between them must be multiplied by the mean value of this cosinus psi. That is what you see here. Okay, so in a specific geometry of the sphere, you can also get another expression which we can let's say which you see that the free daons are very many around the charge, and the daons within the electron, which has some efficiency, let's say, are quite few, which means that if you have a sphere, you can put a perfectly ordered daons on this sphere minus the free daons at the same on the same sphere. And since the free daons are much more than the ordered daons, you will have this free daons interaction penetrates the electron completely, and you get this kind of equation. And you have then an equation for the mean cosine psi of the interaction in this way. You can go a further step, we will do, and we will introduce a new parameter which we call order. and the order is just the mean value of the cosinus psi. It's much simpler. We define this as a O for order, and this is much simpler to express in the formulas, etc., just to simplify things. So we get an expression for this mean value of cosinus psi in the case of a sphere. Okay, so if you introduce this, and you obtain some specific force between the outer layer of the electron. So let us imagine that you have two electrons at a certain distance from each other. The distance should be much bigger than the reference radius of the electron, which is, we write this R here infinite. When you have that the two electrons in an interaction, you should put them so far away that you don't have a variation of this reference radius of the electron. It should be constant. And in this case, you have what we said before, you have that the force between layers is a constant, which means in fact that you can make calculation over any shell of the electron as far as it is far away from the electron center. So you get a picture like this. You can simplify the schematics of two electrons under interaction. You have then that the electrons are so far away that you can put it a straight line and integrate over one shell of the target electron. Well, the shell, of course, must be at a certain distance from the center of the electron, but it could be very small if the distance between the electrons are relatively big, which you see here. We do this because in this way we can access the formulas that we know of electric field and energy. So we can calculate then this force between the shells already, and as you see in this equation here, this Fs is the force between two shells, and the O is the order, and the theta is the angle between the radial rotational axis of the electron from the source electron relative to the rotational axis of the target electron. If you do this, you obtain a nice little formula, and you can, with using an interval at certain distance, then you obtain a small, quite simple formula, and you can then compare this with the definition of the classical formula for electrostatics, and you obtain the Coulomb constant. As you see, the Coulomb constant in the DAON theory is the force between the shells, which is a constant, divided by 3 because of geometry simply, and multiplied by the radius of reference square divided by the electron charge square. This is to compensate for the charges in the classical way of describing this. So it's now possible to redefine certain concepts. So we have that the charge is just an integer number. It's the number of radial equilibrium. It could be plus or could be minus. So for the electron, let us say it is -1 simply. You have the electrostatic force that is defined using the Coulomb constant that we have defined. So this is just the action between the superimposed daons from the source electron calculated over a sphere of the target electron at a certain distance away. The electrostatic field is proportional to the order, and which coincide an electric static field line corresponds to the direction of the rotational axis of the daons. And the electrostatic energy is just the number of effective daons multiplied by c square. So if you have two electrons, you add mass or add daons, and if you have electron and positron, you reduce the number of daons involved. So you multiply these differences with c squared, and you obtain the electrostatic energy. So it's rather simple. Another very important thing is to look at the effective values of this. If you take 1 megawatt per meter electric field, which is very strong for us, this corresponds to an order of 10 to minus 15. So this is, we just touch very softly the extreme strength of the order of the electric field close to the electron. We are really just nudging it slightly. I mean, so this is very important. This is forces within or close to the electron are extremely strong, and we are just sucking at a bit the drop from the ocean. So we end up with a picture of the interaction between an electron and a positron. You see, it's quite nice, and you should keep this in mind because we will later come back to this type of images. And okay, so after this we will have a look at the electron's mass and potential energy. We will try to go a step further. We have still not understood exactly, for instance, what is the value of the reference radius for the electron, and what is its mass. We have the daon is associated with some sort of mass. It should also have some size. So what is the size or radius of a daon? And to understand this, we have to go a step further. So we make first we make some we can calculate the mass of an electron, but as you see here, it's I just present the integral. You can do this numerically, which we will do later on. But if you go some distance away from the electron, then you come into the region where you can neglect the difference of the reference radius, and in this region you can then calculate the mass, which you see in this way here, and you compare this with the classical expression for potential energy or mass, and that gives us the constant that you see here. And this constant is it's the constant in front of the interaction between daons. So you can rewrite the interaction between daons in a more precise way, as you see in these equations here. So 3r for c squared divided by the radius of the daon times the cosinus psi. This is the interaction which are attracting or repulsing the daons from each other. And you have also sinus psi, which is the transverse corresponding force. Okay, so we can have a radial equilibrium of force a bit distant from the electron, which you can now express in this very simple way with that force infinite, and it is far away from the electron, so you have this force between the different layers of the daons. And you get the expression for the Coulomb's law complete in this equation. We are still lacking the value of the reference radius, the size of the daon and its mass. To obtain this, we made a small computer called EP. This is not so difficult to make. I mean, it's since the electron is a perfect sphere, we just impose a certain number of spheres, a certain distance radius from the electron, and using this formula, which you have already seen here, we can calculate the interaction between them, and we obtain a nice equation which we can use. And so first you make this in several steps. First you make that the force between the different layers is a constant, and when you close into the center of the electron, you reduce the number of daons. So you have some strengths of order to compensate for this, and when you come very close to the center of the electron, Then you have also to take into account the curvature, which is a problem. In fact, it's not so easy to do, and it leaves the center a bit vague. In any case, you can calculate. Sorry. Then you have to compare this with the mass calculation to see if that you obtain the correct mass, same mass as for an electron that we know. And when you have done this, then you can obtain the reference radius of the electron, which, as you see here, is 1.23 10 to minus 15 meters. So this is approximately the radius of the electron. And if you look then to the center of the electron, you can reduce the number of daons so that you come to the center of the electron, where the daons is very few, reduced to nothing, let's say. And in this way you can get an expression for the mass and the radius of the daon. So you have the mass of the daon is some 10 to minus 40 kilos, and its size is about 10 to minus 18 meter. So you have that the size of a daon is about 1 part of 1,000 times smaller than the reference radius of the electron, which means that within an electron you have something like 1 billion effective daons. Okay, so this 110 to minus 18 is a free daon size, not the center of the electron. The daons are smaller than this, but what is important for us is free daons. This is used everywhere. So this is the value of the free daons. Okay, so we should know also here that if you, in the formulas, very often you see the mass of the daon divided by the cube of the radius of the free daons. And this is quite precise. The value is about 3 digits, like for the reference radius of the electron. But if you take the individual ones, mass and radius, free daon radius, individually, then the values are much less precise, because of the problem at the center of the electron, that you don't really, it's very difficult to make a correct calculation of this, because the reduction coming down to a small number of daons makes the geometry different, etc. This becomes quite complicated, which means that you are not very precise to know when this last couple of shells are starting, or you must have some gradual or more. It's a difficult problem. So this is less precise. It's individual, so this is not maybe 2 digits, maybe, yeah. not very good. Curve that's going from 1 and then coming down to 0. This is the order. In the center of the electron, you have a very high order, close to 1, and then it goes down to closing into 0, let's say, when you come further away. And then the other two are the charge and the mass. So the higher one is the charge, and the lower one is the mass, which you see is growing with the distance from the electron, both the charge and the mass. You see the charge rise asymptotically to charge 1, and the mass is a bit lower, but it continues until some specific value of the electron mass. Well, okay, so this is now finished here, and of course the next video we will dedicate to the magnetic field and explains how the magnetic field is working, and this is quite important for the following. I mean, electrostatic is not so difficult, it's quite understandable. The magnetic field, which is in discussion for modern physics, I don't really know what it is, but this is very important to understand the magnetics, because it will be used later on in the atomic physics part. Okay, so welcome to magnetism in the next video.